So let's see a quick example of a sample problem on B plus trees. In this question, we have been asked a completely full B plus tree with n equal to 3, L equal to 3, and height equal to 2 has how many nodes? So basically, we are at full capacity. So how we can solve this problem is we know there are three levels in this tree, which is you have the leaves, then some level 1, and then there's some root element. Now, since n is equal to 3, it's a 3-array tree, which means it can have at most 3 children. So that means the root will have just 2 keys, because if it has 2 keys, we know everything on the left in between these two values, and the third child will be whatever is on the greater than the second key in the root. So the level 0 will have just 2 values. Next, the level 1 will contain 3 nodes, because now it can have like 3 nodes that can be attached to this root element. And each of these 3 nodes will have at most 2 values, because it's going to be like L minus 1 in this case, just for the internal nodes. For the leaf nodes, it can store exactly like 3 values, like up to 3 values. So for the internal nodes, it's going to be just two different values, because otherwise it will break the consistency of a B plus tree. Finally, the total number of nodes in the level 1, it's going to be 3 nodes times 2 values in each, which is the 6 values. Finally, in the level 2, you are going to see there are going to be 3 different values in each node, and we have 3 nodes per node at the level 1. So you basically are going to have 9 different nodes, and 9 times 3 is 27. Now we subtract this value 6 and 2 from this, because these two values like 6 and 2 are basically repeated. So the total number of unique nodes that are going to be in this question is going to be 19 in level 2. Also, you can think about it conceptually that all the elements in the leaf are going to be unique. So if you just consider the total number of nodes in the level 2, that's going to be the same answer. So you'll get either 27 through one route or the other. So it's basically the same. So let's discuss a use case of B plus trees. So when I was describing B plus trees, I give you a hint that B plus trees are commonly used in database systems, file systems, and databases. If anybody of you will take a database class later on, you're going to see all databases are typically implemented. They have some form of B plus tree. And why this works exactly is when we talk about maintaining the memory, which is like memory have two or three different types, right? Like you have this cache, which is faster. uh, you have the registers, which is even faster. This is like the CPU. And then you have some sort of main memory, which is our RAM. Finally, we have hard drive, which is the bigger chunk, which is all the data that's stored in the hard drive. So this B plus tree, it's used much more like when we are implementing a file system. And why that happens is because I'll give you a concrete example. So let's talk about just the hard drive. Now, when we talk about hard drive is divided into tracks. Like I'm talking about this physical hard drive. It has been conceptually uh, implemented in the form of different tracks. Also, this has like different sectors. So you have sector 1, sector 2, sector 3, and so on. So this entire chunk, which is like, if we talk about this is one sector. Now an intersection of a track and sector is a block. So this is just one block. And usually, like whenever we are implementing a B plus tree, what happens is this one block size defines one the number of keys, which is, let's say if the block size was 128 kilobytes or something like that, the L is going to be 128 kilobytes, because we are going to define all the leaf nodes such that the leaf node's size is equal to the size of one particular block. And why this is important is because, like, let's say if we want to find out something about a particular file in a block, like let's say if we have this block, we want to find out or search this particular block. Our physical memory, or the main memory, doesn't have the space to bring all the data from this big hard drive into here, which is, like, let's say we have 1 terabyte of data in this hard drive. I have to find out some information in this hard drive. I can only bring some chunks of data, right? So in order to bring some chunks like this, if we implement this in the form of BST, it is going to take a lot of time, because we are going to first bring the block, find some information, go back, bring another block, look for the information if we have found or not, and so on. So it's going to be a lot messy. So how we can solve this particular problem using B plus trees is by creating indices, which is, you basically have an index. Like, let's say if this block contains some database that contains like student IDs and some values, which is some attributes, which is name and so on, name, address, and different things. So instead of keep bringing the whole block, what we can keep in the main memory is just the student IDs. So we create like SIDs. All the SIDs are stored here, and these indices point to different block locations, which is, let's call this like, one is pointing to one block, two is might be pointing to another block, and all the values between 3 and 4 might be pointing to another block. So if you invert this problem, like, what you have is a B plus tree, which is, the hard drives basically look as the leaf elements. These indices act as the internal nodes, because we keep a track of where we are trying to find information by going towards left and right. Now these indices itself can become very big, because let's say if we have millions of files, these indices can be large. So we can create an index of an index, which is, let's say if the student ID is between 1 and 100, so 1 will point to this particular index. Everything between 1 and 100, it's going to point towards like another chunk in the memory, and then after 100 it might be like 101, that might be pointing to another. So basically, if I just delete this, our B tree can act as a multi-index structure to implement a memory, which is, at the top we have some central element, and whatever is on the left is going to be the IDs from which are lesser than the central element, and whatever is on the right, it's going to be greater. And the actual files that we have in the hard drive are stored in this last node. So the last thing I want to discuss in this video is the performance of the B plus trees. We are not going to cover the analysis of this and how we have come across this, but typically the height of this B plus tree is either equal to log of L plus 1, log of n base L plus 1 in the worst case, 2L log of n base 2 in the worst case. So we are not going to cover the analyses because it's outside the scope of the class, but the largest possible height that we can have is based on L divided by 2 items, while the smallest possible height that is possible is when we have L items in a particular node, which is, like, let's say if we have this tree, and if this is just like a BST, so then the height will be much more compared to if we have like like let's say if we have 5 nodes, we store this in the form of BST, then the height will be worse because we have not utilized the capacity. But if we have more keys in the nodes, like earlier we had 5 nodes, what if we can also store 5 nodes in the form of this, right? So height will be less. So the minimum height that's possible is dependent on how many keys are stored at any particular node. So the overall height for a B tree or a B plus tree is O of log n. Now the search time is O of HL because it's dependent on height, as we saw earlier in B trees or B plus trees. Now you have to also search n elements in a particular uh, L elements in a particular node, because this can have at most like L elements. So you have to search that. So this can be actually simplified to log n because L is going to be a constant that is set by us. So we can perform most of the common operations in O of log n. But this tree is widely used because there are some problems that cannot be just solved by AVL or B plus binary search trees. In the next video, we are going to cover our next data structure, which is the splay trees.